to the application of that. Now, let's say we use R just straightforward, and we just want to create a model here, and we want to predict first year college GPA from ACT plus the district. Now, before I hit enter, I'm going to tell you what's going to happen. It's going to select one of these. So it looks like to me over here on the spreadsheet, we have, what, A, B, C, D, I believe. I think there are 4 school districts. I believe there are. It's a huge data set. I'm pretty sure. I'll tell you what, I want to confirm that before I... So yeah, we have 165 in A and 149 in B and so on. So I have 4 school districts. So now I want to create my model. Sorry about that. I just wanted to make sure. Now, let me tell you what's going to happen. Our output is going to have 4 predictors. Well, it's going to have 5 predictors. It's going to have 5 lines. It's going to have 1 line for the intercept. It's going to have 1 line for the ACT, and then it's going to have 3 additional lines for the district. What's going to happen is you're going to see that one of these districts isn't going to be included because that's going to be our reference category. So the other 3 predictors, the dummy variables, are going to be a comparison to that predictor. So, well, that's fun. What did I... Oh, I did GPA as PGA. All right, whatever. Got PGA on the brain. Maybe I got some golf on the brain. It is almost time for the Masters, so cool. All right, so exactly what I said would happen. Notice the District A isn't included here. So District A is the reference category. So how do we interpret this line right here? Well, this line right here would be interpreted as controlling for ACT and District CA comparison and District DA comparison. Now, an increase of 1 unit tells us what? We're comparing from District B to A, right? So a negative tells me that District B is lower than our comparison group. So we would say the predicted first year GPA or first year PGA. I just do it like this. The predicted first year college GPA is 0.056 lower for District B than for District A. Now, a couple of nuances here. What if we want to compare District B with District C? Well, we can't do that with this analysis. We would have to run another analysis to make that happen. Now, and shifting the base group is easy. I can just recode district, and I can use the relevel. So I can just put district there, and I can put what do we use there? I forget what we call that. I'm just having a complete brain freeze here, and I'm not even eating ice cream. Is it level? I'll tell you what. Let me get some help on the relevel. This is kind of good. It happened. So reference. That's what we need. So relevel. We have our vector, and then we have our reference. Typically a string. All right. So district recode. We want district. Oh, shoot. Yeah, there's something going on outside, and it's got me distracted, and it's not cool. So reference, okay. All right, I'm back with you now. I promise. District recode. Relevel. We want to district reference equal, and I don't know, let's just say we want this to be C, whatever. Man, somebody's knocking at the door. Okay, I see what it was. It's a UPS guy. I was putting up a video earlier. My next door neighbor just walked right in, and I'm like, glad I wasn't sitting here in my underwear or something. So anyways, just too much going on for me to stay focused. Now, sorry about that. So if I want to go back up to the model, and instead of using district, use you can probably hear my Arlo, my security system going off because of all that's going on out there. Okay. All right, so what you can see here is because we set the reference equal to C, then we have all of our comparisons to C. So this would be an A to C comparison. This is a B to C comparison. Of course, this is a D to C comparison. Interestingly, District C must be a high-performing district because all of these estimates are negative, indicating that controlling for the ACT, that the predicted first-year college GPA would be lower for A, lower for B, and lower for D. So I'm glad I lucked up and chose, even through all the clumsiness, that I chose reference C. I lucked out there. Now, how do we do all this in R and with matrix operations in general? Well, the first thing we would need to do is set up our dummy variables. So what I'm going to do here is I'm going to establish, first of all, my reference. I'm going to just let C be the reference. All right? So D1 will be is A to C comparison. My dummy 2 is B to C comparison. And D3, of course, is D to C comparison. Now, I think this is doable in R, but I think it's a lot more complex than just taking care of it over in Excel. So what I'm going to do is I'm going to just sort my expand the selection with my districts, and using some just convenient fill down, it works nicely. So I need my first dummy variable, second dummy variable, my third dummy variable. So every place that I see an A to C comparison, since dummy 1 is the A to C comparison, when I see an A, I need a 1 in the D1, and I need zeros in the D3. Now, the beauty of it is all of my A's are going to be the same structure. All right, what do I want for B's? Well, it should be pretty obvious that I want my dummy 2, because the dummy 2 is B to C comparison. Again, I think this is the easiest way to do this. What will C be? Well, C is going to be all zeros, because we don't have a C to C comparison. Some people may say, well, this is an awful simple approach to, surely it's harder than this. One of the most commonly missed problems on exams and assignments in 5500 has historically been problems that have dealt with setting up dummy variables. Because what I'll do is I'll give you, on an exam, I'll give you a very small data set, 6 subjects maybe. And I'll have you set up the dummy variables in the design matrix, just by writing it out. Okay, so we have the dummy 1, dummy 2, dummy 3, dummy variables set up. So now I'm going to save this as something new. So I'm not very creative, so I'll save it at that. And now I'm pretty much set. So I need to, I'm just going to go back up and I don't know why all that's there. So I'm going to so I have ACT with CSV. So when it comes to following objects or masks, what that says, just tells you, is that these variables are kind of put on hold, if you will, because they were used in a data set that was previously attached. So typically, a red warning from R means we've done something wrong, but we haven't here. I just want to take a look at the new data, and you can see that we have our dummy variables now. Okay, now, as we should expect, transitioning into matrices, we're going to set up a Y matrix. So we went first year college PGA. In row, I don't know. Let me back up here. So we have 7, well, okay, we have a huge data set. So my Y is going to be matrix, first year college PGA. In row is 705. In column equal 1. By row equal false. All right, now we need to get our design matrix. So same game. Multiple ways to create your ones. This is the way I do it. There are other ways, obviously. So I need to C-bind some stuff. So I need my 1s, I need my ACT, I need my D1, my D2, and I need my D3. Notice that I no longer use my district of A's, B's, and C's. Again, in matrix operations, that is completely irrelevant to us. in columns are going to always be equal to the number of things that we're estimating. So we have 5 there, right? Now the last thing I want to do is look at the X matrix, because it's going to be a 705 by 5 matrix, so it would just clutter up the desktop, or not the desktop, but the output, and I don't want to do that. All right, let's grab our B. So we know that. Look, there's something else I wanted to show you before I went into this, but yeah, well, let's just let this happen. So our beta should align with what we have before. And well, this works out nicely. It's where we don't have to even look at it, so we can see that our betas are the same. That's pretty good, because it'd be pretty goofy mathematics, matrix operations, if it gave us something different. Now, again, I can't emphasize this enough, and I think I've said it a lot. Once we get the operations down for simple linear regression, with just a few modifications, specifically to the design matrix, all the other calculations follow suit, right? For example, if I want the structure of my variances for my betas, they're called the variance covariance matrix for the our betas. Well, we know that we can do that with the mean square error. So I would create the I would just run the ANOVA of our model to get the mean square error. It's kind of cheating, right? But so it's 0.348. So the variance covariance for B is going to be the mean square error times the inverse x. So what do we have here? What's the first diagonal? That would be the variance of beta 0. This is the variance of beta 1, which in this case is ACT. This is the variance of our dummy variable 1. This is the variance of dummy variable 2, and this is the variance of dummy variable 3. You can see that our standard errors are very, very, very small, as demonstrated by our output. All right. Even though we're in a multiple regression perspective, we can still calculate our predicted values. And probably the easiest way to do this, remember, we can use our hat matrix, but we haven't calculated it yet. So the simplest way to get our predicted is just take the design matrix times our beta. And I'm not going to do y hat, because we would have 705 elements there. Our errors again are easy to calculate. It's just our observed minus our predicted. So our observed would be the first year college PGA minus our predicted, so just y hat. If we want to look at a histogram of our errors, again, is that a normal distribution? No, it's not a normal distribution. Don't say that. But it does look like this distribution, which is a sample of our errors, does. It's reasonable to think that this does come from a normal distribution. So the normality of our errors, I think, is reasonable. Now we could get a QQ plot as I've demonstrated previously, but I'm not going to get into that because I think it's time to end this video. I can't think of anything else that I really wanted to calculate. Well, I'll tell you what. Let's do one more. Let's do the variance of our errors. If you already know how to do this, feel free to terminate the video, stop the video, and go on. So we know with the variance of the errors, the variance covariance matrix, we need the mean square error. We need the identity matrix. So the identity matrix here is going to be the diagonal. We need 705. And we need our hat matrix. So to create our hat matrix, we need X inverse Now our hat matrix is going to be huge. It's going to be 705 by 705, so we don't want to go there. So the variance covariance of our errors is going to be the mean square error times our I minus our H. Now it's going to be a huge, I hesitate to do this, but yeah, I don't even know it's going to print them all out. But, just to give you an example, yeah, that's why I don't like to do this, because it just overwhelms the output. Goodness gracious. Of course, 705 by 705 is, a huge matrix. Well, this is fun. Remind me never to choose a data set this large again. Not that you can remind me, because these are recorded way before you get them. Well, we having fun yet? All right, finally. All right, so what does this first entry give us? It gives us the variance of the residuals for the first case. What does this value give us? It gives us the covariance of the residuals for the first case and the second case. So, sorry about that, guys. That was just insane. I'm done.